morning, friends. I welcome you all here for my course, Engineering Thermodynamics. As of now, I have already completed the basic concept like systems, surrounding, micro level thermodynamics, macro level thermodynamics, properties of the fluid, steam table, these all things, and heat and work, the concept and derivation for the work, I have done it. From last 2 classes, I have done 2 numericals related to the heat and work, that is part 1 and part 2. Today I am on the heat and work topic, and today I am going to take few numericals, and that I have given as part 3. Here, this is my content for the day, and in this I have the numerical problem 1 to find state points and work done of single piston cylinder arrangement with double spring. That is the first problem. And the second numerical problem to find state points and work done of double piston cylinder arrangement with single spring. So here you can see that in the first case we have the single engine, single piston with double spring. In the second case we have the double piston and the single spring. So here 2 opposite type of problems are there, and this type of problem really it is happening in the society or in environment or any engineering application. This type of situation may arise. Whatever problem I am here solving, this I have taken from the Senegal book, that is Engineering Thermodynamics, and these are also given in some NPTEL lectures. So I will go for my today's problem, and here as I told you that in this we have the single piston. This is the piston here, and this is the spring 1, and this is the spring 2. So we have the double spring, single piston, and here it is P0 is a atmospheric pressure. Here is the here the system is the ammonia here. It is, so first we have to understand this diagram, and then only we should get, this is from reference 1. So here first I will read it, the problem. So here 2 springs with the same spring constant, that is the spring constant K is same, are installed in a massless piston cylinder arrangement. So this piston, it is massless piston is there with the outside air at 100 kPa. So this P0, this outside air is 100 kilopascal. This is given. If the piston is at the bottom, so assume that piston is just touching here at the bottom, means there is no volume. This is given. If the piston is at the bottom, both springs are relaxed. So in that time, when it is at the bottom here, your piston is here, no spring is touching. Both are free. Both springs are relaxed, and the second spring comes in contact with the piston at V is equal to 2 meter cube. So as and when it is coming in this level from here to here, this is the 2 meter cube, and the first spring is going to touch that time. The cylinder figure below contains ammonia initially at -2 degrees centigrade and X. So here temperature T is given as a -2 degrees centigrade, and the quality X1 is given 0.13, and the volume V is equal to 1 meter cube. So in this condition, it is given, which is then heated. After that, after touching this, it is heated till the pressure reaches to 1200 kilopascal. So it is heated, so the pressure will rise to 1200 kilopascal. So what we have to find out, at what pressure will the piston touch the second spring? So at what pressure this will touch this second spring or not, that we have to find out. Find the final temperature and the total work done by the ammonia. So we have to find out the P2 and the final temperature T3 and the work done. These things we have to find out. So this is the problem, and this we have to solve in a given sequence. Very interesting problem and very practical. This type of springs are used in our railways, wheels and all. They are also the same pressure. It doesn't mean there will be a piston, because the wheel is touching and your spring, your truck is spring. Your bike or vehicles also, it is like this. Your shock absorber are like this. So we can, these all problems are the practical problem which every engineer has to face in the real life. So we should take care of, we should understand the problem, and then we have to solve the problem. So now here, first we should draw the schematic of the problem. So here, this you can see here that this is the spring 1. Spring 1. This is the piston. And this is massless. So MP is equal to 0. This is the spring 2. And here is the P0, atmospheric pressure here. So we have to find out, and we have to see what is the state of this, our state 1, then state 2, and like this we will proceed ahead. Few things are given, and remaining things we have to find out by the help of the tables, ammonia table, because here this is the piston and here is the system. This is the system, and system is ammonia. The system is ammonia. Here it is a control mass system. Your mass will remain same at all conditions. Whether this piston is here at the bottom or here, at any point, the inside ammonia, the amount, the weight, the mass of the ammonia will remain the same. It will not transfer. So it is a control mass system. In control mass system, the mass will not change the boundary of the system. So mass will be same for all the conditions, and this gives a very good result when we solve the problem. So here we will see that state 1, the system is ammonia, that is NH3. Temperature at initial, it is given as a -2 degrees centigrade. So the ammonia will be in two-phase system, because ammonia, it is like a water. It will be also in the two-phase system. It means first it will be liquid, then it will be the vapor. So liquid and the vapor, if both things are there, we call it as a two-phase system. Here we cannot use directly the ideal gas equation, because this ammonia will not behave like a ideal gas, because it will change its shape, its phase from liquid to gas, gas to liquid, and from gas to superheated gas, and so on. So we should be very much careful that we should understand that what type of system is there. If it is air at a low temperature, low pressure and high temperature, we can assume that it is an ideal gas, and we can use the ideal gas equation. But if it is ammonia or some refrigerant and all, or water, we cannot use the directly gas equation. So we should be very much care while using the equations, and also when we have to use the gas tables. So here it is ammonia. Ammonia is in two-phase system. In two-phase system, we cannot use the state equations or the ideal gas equations. So we need to find here. So being that two-phase system here, two-phase, we need to find Vf and the Vg. Vf is what? It is a specific volume at liquid state, saturated liquid, and this is the saturated specific volume at saturated gas. So if I draw like this, just you can see here and you can understand that this is our two phase. This is the P and V or T and V. So we can see that this phase, the volume is Vf here, and this is here at a constant pressure. This is the Vg. So this Vg indicates that it is a saturated gas, and here this is the saturated liquid. So here we have to find out Vf and Vg, because Vf and Vg is not given. But how to find out this? By using the ammonia table at -2 degrees centigrade, because it is given that ammonia at -2 degrees centigrade, we can find out what is the Vf and what is the Vg by the ammonia table. And we have seen in our previous lecture, we have derived, we know the equation of volume, that is V1 is equal to x1 Vg1 plus 1 minus x1 Vf1. So we can find out this V1 at given x condition. X is given, x1 is given. So if you want to find here x1, what is the volume? So we should know this Vf1 and this is the Vg1. And we know this. So we can find out directly, because we have got Vg1 from the steam table and Vf1 from this ammonia table. We know the x1 is given 0.13 here. X1 is given. So here we can write here that V1 is given 1 meter cube and x1 is 0.3. So we can get V1 by putting the value of Vg1 and the Vf1. So total volume is given 1 meter cube and V1 we have got. So from this we got the V1 is given, and V1 small V1 specific volume we have got from this equation. So now we can find out the mass. So how much is the total mass of ammonia? Mass of ammonia, that is M is equal to V1 by capital V1 means total volume divided by the specific volume, which we have find out by this equation. You put this value and you will get. I have not put here value. You can do by yourself and you will get the result. My objective is to give the concept, not just putting the values, because it will take a lot of time, and I think everyone is able to do. You can all find out the Vg1 and Vf1 from the given table, which I have described in my some previous classes, that how to find out Vf1 or Vg1 for a given gas. So now we can find out the mass. This mass is equal to V1 by small v1. By this we get the mass of the ammonia inside the cylinder. So this mass of ammonia M we have got from here, this equation. I think it is very much clear. So as of now we have find out the mass. And why we need to find out the mass? Because this mass will be everywhere same. So in the next we will put M is equal to something and we can find out the another state. So that is the objective of this, finding out the mass. So now we have to see here that by the PV diagram here. So what is the P1? So in this state, what is the pressure at the 1? So this we can see here how this will go. If you draw the P and V diagram, so it is given that at the bottom, this is the bottom, when the piston is, just I am drawing here, when this piston is just touching, this is the bottom here, I will just, this is the piston at the bottom. First, it is a hypothetical case, and in this case you don't have any volume. So here volume is 0, and here is atmospheric pressure, it is given. Okay, so we got here, this is the 0 point, and it is a hypothetical point. Okay, it is just for our making our problem easy, we got this point. Also, we have, it is given that V1, so we have to have minimum 2 properties to get here. So here we got temperature T1, we got minus 2 degrees centigrade, and V1 we have calculated just now. 2 properties we have got. By this 2 property, we can get how much is the P1. This is the P1. This is the here P2, and this is here P3. Okay, so this is the saturation pressure corresponding to minus 2 degrees centigrade. So what is the P1? P1 is the saturation pressure at minus 2 degrees centigrade from the table, and we got it by the table. Now, if you draw the PV diagram, we can see that when the piston touches the spring, here is the spring, so initial condition, and the next is, this is a P1 condition here, this is the P0, and this is the P1. So here one is touching but another is not touching, and here is the atmospheric pressure. Okay, so when the piston touches the spring, the reinforcing force will be double. So when this is touching, reaching to this condition, both will be touching. So now the kx, the force will be 2 kx, not 1, because initially it was kx. So the spring force will be double as there are 2 springs. So from the point 2, the slope will be double. So up to 1 to 2 means from here to here it is okay. But as you reach here, so this was the initial slope. From here, this slope is increased, and this slope will be 2 times. So I have made like this. This is the 2 to 3. This condition is given. So we can find out the another states by using the equations of straight line. So from the point 2, the slope will be double up to 0.3. So here this slope is double. Actual PV diagram will be 1, 2 and 3. So from here to here it will be a straight line. From here the slope, this is the slope. So here you have the more slope, means it has the double slope of this. This condition is given, and for this only P0 is given. P0 is only to find out this point, not anything else. So we have got this, that point 2 not known, only volume V2 is equal to 2 meter cube is known. Okay, so for both spring have the same spring constant. So using equation of straight line, so we can see here that P3 and P2. So P3 minus P2 is divided by here V3 minus V2. V3 minus V2 is equal to 2, means it is 2 times P2 minus P1 means the slope. 2 times P2 minus P1 divided by V2 minus V1. So here 2 times, it is given that 2 springs are there when it is touching this spring. So now we got this equation, and from here if we can see that from hypothetical data point 0, it's a straight line. So using equation of straight line from here 0 to 2, we can find out that P2 minus P0 divided by V2 P1 minus P0. So P2 minus P0 divided by P1 minus P0 is equal to V2 minus V0. V0 is equal to 0 and divided by V1 minus V0. So here it is touching, so it is 0 and this is the 0. So here we know the V2. We know the V2. So P2 minus P0, P1 minus P0. P0 is atmospheric. This is also given. Okay. And P1 we have find out from here. So we know this everything we know the V2, we know the V1, we can find out the pressure P2 directly by the putting this value. So from equation 2, we can get the pressure P2. So pressure P2 we can get it. This we can see here that this is the line and this is the line 1 and 2. So this we know, we have got it. We know this P2 we can get it. So we got the now P2. And V1 and V2 are given in the problem. And this V1 is given, V2 it is 2 and it is the 1. Meter cube, meter cube. So we can get the P2 from this equation and we got that 694. Here we got 694.875 kilopascal. And this is the atmospheric pressure. So this value of P2 we need to put in equation 1. So we get the value of V3. So here if you see in this equation now, we know this P2, we know the V2, V3. Okay, so these all things we know, and if we put here, we can get the volume of V3. We can get this volume V3 by equation 1 here. So here we can get this V3. This we will get. Other things are given here. So now we got now V3. Now state point P3 is given. V3 we got, it is a total volume divided by mass. Mass we have already calculated. I think you know V1 by small v1. So here V3 we have got from here and divided by, we got this also. We got two properties. To locate your point 3 here, we have got here P3 into V3. We got here. So if you know these 2 points by the table, we can get the temperature. So using the P3 and V3, we can get the temperature T3 from the table, ammonia table, and we got the T3 is equal to 51 degrees centigrade. Please do the calculation and you will get the same result. So try to do in your homework, try to practice it by using the table. Now we have got the specific volume, we have got the T3 at the final stage, and we know all the P1, P2 and P3, everything we have. Now we can use these values to find out the work done, because for the work done we need pressure and the volume, then only we can find out. Temperature is not concerned. So now we will calculate the work done by this system. So here this you can see that we have got this P1, we have got this P2, this is the P3, V1, V2 and V3. So here we have, this is the one trapezoidum and this is the another trapezoidum. So now we know that work done is equal to total work done from 1 to 3 is equal to work done from 1 to 2 and plus work done from 2 to 3. So here for the first trapezoidum, 1 by 2 P1, this one P1 plus P2 into V2 minus V1 plus half P2 plus P3 into V3 minus V2. All the value we know, all the values are we have find out. Putting this value P1, P2, P3, V1, V2, V3, we will get the work done. Work done by the piston is 1342.6 kilojoule, and this is a positive work. It means what? Work is done by the system. Work is done by the system. So here is the system, here is the piston, and here is the system. So if it is pressing upward and this is moving, increasing the volume, then it is a positive work done. So it means if you are getting the positive work done means the volume has increased. So cylinder was from here and it is increased from here to here, means that it is able to supply the power outside. The surrounding will get the power from the system. So that is the analysis for this result. It is our duty to understand the concept, not only the numerical value, but by the numerical value, what you can assess, what you can do analysis. This is also very important, and this will come only when you have the sufficient conceptual knowledge on the theory behind the problem. So here I have completed the first numerical, and now I will go for my second numerical, and hope that is also very, very interesting. And try to practice in your home. Try to use the steam table, try to use the ammonia table, try to use the refrigerant table in your home and find the answer. If you are able to find the answer, it means you are doing the correct. And without making PV diagram, you cannot solve the work done. To solve the work done, you need to draw the PV diagram. Then only it will be, result will come correct. Directly putting the W is equal to PdV, you will not get. Because if you are putting directly, this line will go like this. So this much work you are giving extra, which is not producing in the real scene. So that we have to ensure that you have to draw the PV diagram, then only you will be able to solve the issue. So now I am going for the second problem, and that is also very interesting. So you know that in the previous numerical, there was only one piston and two springs. Here the case is different. Here we have the two pistons and one spring. So just I am reading my problem, and then we will go and do the then we will solve the problem. A cylinder, the area of the cylinder is 7.012 centimeters square, has two piston mounted. So in this, I am writing P1 and I am writing P2. There it was S1, S2. Spring were in the previous S1 and S2. Here we have the P1 and the P2. Piston mounted. The upper one has got 100 kg. So mass of this one, it is called P. The upper one is MPL is 100 kg, and kg initially resting on the stop. So this is the stop here. This is resting on this. The lower piston MP2, this is MP2 is equal to 0. Mass is 0, massless. Has 2 kg water below it. So here this is the system. And mass of this water is 2 kg. It is given. With a spring in a vacuum connected the two pistons. So here it is a vacuum. Vacuum means we can understand that no atmospheric pressure. P naught is equal to 0 here. It has a spring in a vacuum connecting the two pistons. So this spring is connecting this piston, and this is massless. It is just supporting. The spring force 4 is 0 when the lower piston stands at the bottom. So when the lower piston is at the bottom, the spring force is 0. So here also one condition, it is a hypothetical. So when this piston is here at the bottom, the spring force is 0 when the lower piston stands at the bottom, and when the lower piston hits the stops, the volume is 0.3 meter cube. And when this is hitting here, the volume is 0.3 meter cube. The water initially at 50 kilopascal, the pressure is given, and the total volume of this thing is given 0.00206 meter cube. So state 1 is given, P given, V given, and the mass given. So if we divide this V by M, we will get the specific volume at state 1. So one state is given, and the second, the volume is also given. So we have to find out. So find the initial temperature. So in the first case, P and V is given. We have to find out the T. It is just refer the table of the water, and in that condition you will get the temperature. Find the initial temperature and the pressure that will lift the upper piston. So we have to find out the initial temperature and the pressure that will lift this piston, upper piston. Means this is 100 kg. So at what condition it is lifting. Find the final temperature, pressure and specific volume and the work done by the water. So these things we have to find out, and we will see that how we can go ahead. It is like the previous one, little difference is there. So that we have to look into. So here I have drawn the schematic of this problem. Here is the water is a system here. This is the piston 1. This is the piston 2. This mass is 0 and MP1 is equal to 100 kg. This is the 2 kg of the water is given. Okay, so before we start the problem solving, need to draw the schematic of the problem. Here we have 2 piston with single spring arrangement as shown here, piston 1, piston 2, and here spring is 1. What the condition are given? First we have to see that as per the problem, what are the conditions are given. So spring force is 0. That is the when the lower piston is at the bottom. So at the bottom, when this piston is at the bottom here, the spring is not touching. Spring is not touching. It is hypothetical state. I told you that the hypothetical state is given to make our problem easy. So we can get that starting point. Actually, that starting point is not existing. It is hypothetical state. When heat is transferred, only bottom piston is moving. So only bottom piston is moving. Let us identify that condition when both piston move together. So as and when we give the heat here, heat, so it is start moving. So at what condition it will? We need to draw the free body diagram. For this, the diagram will look like this. So this you can see that this is the MP1. It is given as 100 kg. This is the MP2 is equal to 0 kg. From here this water is giving the pressure. So it is a pressure P into A, and from top it is atmospheric here, P0 into A here, and here we have the MP1. It is acting downwards. I am just putting here MP1, and this is massless, so no use of putting this. Fx also in the downwards because it is trying to push down, so Fx is also in this direction. So we can do this thing that PA is equal to P0 A plus MP1 into G plus MP2 into Z. So here we have PA is equal to P0 A plus MP1 into Z. So here we can see that P is equal to P0 because initially it is not touching. So spring is not here. So here P is equal to P0 plus MP1 into G by A. A is the area, it is given, and this is called the P lift. This will try to lift. This is the P lift. It is trying to lift this, and here P is given 1500 kilopascal by putting given values. If you put this value P naught plus MP and A, you will get 1500 kilopascal. You will get this P. So it is pushing upward by 1500 kilopascal. Okay, that issue we have got it. Now draw the PV diagram. We should understand the state as in it is in two-phase system. We have to draw a straight line from the origin. So here it is, volume is 0 here, and so here we have to draw the straight line like this. So here what is the given? P1. P1 is equal to 50 kilopascal. V1 is equal to total V1 by mass. Mass is given M and V1 is also given. So we will get a specific volume. V1 is equal to V1 by M. So you will get 0.000103 meter cube per kg. So let us calculate for this. So here is straight line from P to 1A to 1. So what we will get here? P1A minus P1. This is the P1. This is the P1A. So P1A minus P1 divided by P1A minus P0 is equal to V1A minus V1 divided by V1A minus V0. So this V0 is equal to 0. P0 is equal to 0. So from here we will get P1A is equal to P lift. We have find out as a 15 kilopascal. V1A is equal to V1. It is given. P0 is equal to 0. So this V1 is given. We have to find out this. This is given, and this is given. So we can find out the V1A. So V1A we have find out, and this value of this V1A is less than V stop. V stop is 0.3 divided by 2, 0.15 meter cube per kg. So this we have got it, and we have seen that this V1A here, this is less than the V stop. Means it has not reached to that, because it is V stop is given as a 0.3. So 0.3 divided by this thing 0.15. But V1A is not that much. So let us find the Vg at saturation. So V stop is given at 1500 kilopascal. So V stop is greater than Vg. So here it is a V stop here, and we can see that this V stop is more than, means in this side, more than Vg. So ahead of the saturation line. So the lower piston will not hit the stop. So in this given case, this lower piston and the upper piston, this piston will not reach to the stop. Somewhere before it will stop here. Okay, because this Vg1 is less than V stop. So if it is more than this, then only it will hit. So Vg1 is less than the V stop. How to find the initial temperature? So now we have to get the initial temperature. We know that P1 V1 as given, so T1 can be obtained directly from the steam table, and we got the T1 is equal to 81.33 degrees centigrade from steam table. From steam table at given P1 and V1. It is already given in our problem itself. It is given. So first question, that what is the initial temperature? So initial temperature we will get 81.33 degrees centigrade. Now how to find out the final temperature, pressure and the volume? So we know that state 2 is equal to V2 is equal to Vg at 1500 kilopascal from the table. So we can find out the Vt. This V2 is equal to Vg because it is like this. This is the 2 and this is the stop. So here it is 1500 kPa. It is given. So from the table we can get this V2. This is the V and this is the P. It is a straight line. It is not a, it is a pressure is constant. So we can get the V2 and this V2 is equal to Vg at 1500 kilopascal. We can find out from the table. And this T2 is equal to T saturation. This also we can find out from the table. So V2 and T2 we can find out directly by the help of, so we got here P2, V2 and T2, we have got it. Now the next task is to find out the work done by the system. So here we can see that the work done 1-2 is equal to W1A plus W1A to 2. So if you see here, so just if I draw like this, so like this, this is the the 1A, 2. Okay, so here this you can see that the 1, so I will just draw some other color, this and this. So work done 1A, this is the rectangle, and another is here. If you, I will draw the, here this is the, so you can see here one is the trapezoidum here and one is the rectangle. So work done is equal to W1, this is the 1 into 1A and plus W1A to 2, and here is the stop. We are not concerned with this. Work done is only up to here, not here, because after that from 2 it is not moving ahead. It is the final state. So half P1, this is the P1, this is the P2, P1 plus P2 into V1A to V1, and this is here, if you see, this is the V2. So half P1 plus P2 V1A minus V2 plus P1A, same pressure here, P1A V2 minus V1A. So this we know, all the things. We will get the work done, total work done, that is WD12 is equal to 348.91 kilojoule. So this we have got the answer. Please ensure that you draw the PV diagram, and after PV diagram only you try to attempt this work done. Otherwise you are going to fail, your results will not be correct. So it is very much essential, first understand the problem, then you draw the schematic diagram, then you draw the free body diagram, then you draw the PV diagram, then only you should try to attempt the question. So Here I have some references. It is not the next topics. These are the next topics, not the references. Sorry. Next topics. So first law of thermodynamics I will be discussing, then energy and the work, then internal energy as a property. So these topics I will be covering in my next class. These are the references. P.K. Nog, Engineering Thermodynamics, Tata McGraw-Hills, then Eunice Sengel, Michael A. Bowles, Thermodynamics and Engineering Approach, Tata McGraw-Hills, and this is the NPTEL lectures. I am referring this also. So any questions you are welcome to ask. My email ID is ydwivedi@. Thank you very much for joining and be tuned for my next lecture. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.